We had this formula telling us how we can use integration to perform sums of this form. So I want to go through a couple of examples of using that with you. The first example is quite straightforward, which is we're just going to calculate basically the length of a piece of string. So let's imagine here's a piece of string of length L, and we'll assume this is the x direction going in this direction, and so it goes from the point, the origin 0 to the point L in x. So the way I'm going to choose to calculate the length is that I'm going to divide this up into tiny little pieces, each of length delta x, and then I'm going to add up the length of those pieces. So what I want to do is I want to do the sum over all of the n bits that I've cut it up into, each of length delta x, and that'll give me the total length. So this is an example of this left-hand side. If I make these delta x bits go to 0, I'll have an infinite number of them, and then we correctly get this side. Except it's very simple, because here fx of n doesn't have any value other than 1 all the way along. So this is just an example of using this formula, where I'm going to integrate over the range in x I'm interested in, from 0 to L. F of x is 1 dx. So we can do that integral. 1 integrates up to x. I place it between the boundary limits, 0 and L, and that's just equal to L minus 0. In other words, the length of the piece of string is L, and that's worked correctly. Okay, let's try and do a more complicated example now. I'm going to assume that this piece of string has a charge density along it, so that's a number of coulombs per metre, which will be equal to k, but it's not going to be the same all the way along the line. It's going to depend on where we are along it. So it's going to look like k times x. So at x equals 0, there are 0 coulombs per metre, but by the time I get out to L, there's kl coulombs per metre. So that tells us, of course, that this constant k comes in coulombs per metre squared. Okay, so if I want to calculate the total charge on this piece of string, I can't just multiply the charge density times the length, because the charge density is changing as I move along the length of the string. What instead I have to do is to break the string up into lots of little bits, so that over any one individual bit, I know what the charge density is. So I'm going to sum the amount of charge on each of those bits. So that's going to be given by the charge density at the point where that little bit is, lambda at xn. And I'm going to multiply that by the length of the bit, delta x, to give me the charge on one of those little pieces. Now I use this formula, taking the limit where delta x goes to 0, I learn that this is equal to the integral. Again, I'm interested in going from 0 to L in x. I now have an f of x n, which is lambda of x dx. And again, we can just now perform this integral. We're going from 0 to L of k x dx. And that is equal to k x squared upon 2 evaluated between 0 and L, and that's nothing other than k L squared upon 2. And just to check that it makes sense, let's do the units. So we said that k came in coulombs per metre squared, L is a length squared, so indeed that is a number of coulombs, which it should be if it's a total amount of charge.